we are looking at the third day of the Cartesian vectors. This is three-dimensional vectors. So what we're going to basically try and do is take everything that we've learned so far and apply it to a three-dimensional scenario. And so what we're going to want to do is just start to visualize three-dimensional vectors, how they go, how they look, how operations work for three-dimensional vectors that we've already learned, things like magnitude, direction, and so forth. How to visualize a three-dimensional vector and draw it, okay? So what we're going to do is we're going to plot some of these points here. So when you're drawing a three-dimensional vector, you're going to draw a coordinate plane that kind of comes out like this. This one, it turns out to be the X and the Y for our textbook. This is sort of like a standard way of doing it, and Z. So this would be considered up, right? This one would be considered forward, actually kind of coming out towards us. And this one would be considered then, I guess, right in a way, right? If this is forward, imagine sort of a person standing here. Sorry, I said right, I meant left. Left. I always mix up my left and my right. So if this is forward, then that would be the person's left, which would be our right, okay? Anyway, so that's kind of the idea there, all right? And so let me get rid of this person and those words. And now what I tend to do is I tend to put a sort of a dotted line for all of the negative values. And now what happens is when you do it this way, it tends to it gives it a three-dimensional feel. It starts to, excuse me, you're allowed to keep track of things a little bit better. So let's draw this this point, 2, 3, -1. So when I draw, I kind of make 1, 2, right? And if so you want to kind of give it a little bit of a perspective. And so the little marks that you do in there, right here, you want these marks here that I just erased, to be parallel to the y-axis. So notice I'm going to put these on. They're parallel to the y-axis. 1, 2. And if you do that, and then the marks that you put on the y-axis should be parallel to the x-axis. 1, 2, 3. If you do that, you would tend to get a three-dimensional look to it, right? A lot of people would put their marks still like this. That would you could do that, but it would destroy the three-dimensionality of the thing here, right? And now what I'm going to do is I'm going to sort of make a dotted line coming out here at 2, a dotted line out here at 3, and right there, the intersection of those two is point 2, 3, right? 2, 3. And now, basically, what we want to do is we want to go 1 unit below that to right there, okay? So I'll erase this point. And basically, our point A is 2, 3, -1, okay? And if you've, this one should be a little bit more parallel to like that. And I'm going to go 1 unit below, all right? Now, this is the first time I'm trying real hard to kind of get that. There we go. So this is point A, right? So you can really see that it's, 2 units in the x direction, 3 units in the y direction and a -1 in the z direction. So it's gone down there. Some people even go a little further and they actually make a full-on box like you would, making a three-dimensional box. So I would draw -1 down from each of these locations, -1, -1, -1, and then you could kind of connect it in this sort of box thing here. And there, now you really have an idea that the point that you're trying to draw people's eyes to is that one, okay? Let's do this one, -4, 0, 2, right? We'll do this maybe in green. So -4 would be 1, 2, 3, 4. 0 in the y direction means I actually don't go anywhere, but I go 2 up in the z direction like that. So I would draw kind of a thing like that, a thing like that, and this is point B here, which would be -4, 0, and 2, right? And if you look closely at that, you can see that that point B is hovering above the x-axis, all right? And so there you have it. So question is, now we have quadrants in the other scenario, but we've got octants now. So this is now an octant, which would be there 8 different ones. And so when you want to like for example, this point A, what octant is this guy in? Well, it's in the forward octant, okay? The left, right? Lower, all right? Down. So you could say it's the lower left forward or lower left forward, A. Whereas B, it's actually not in an octant. It's, you could just say that it's in the back upper, I guess, neither left or right. So basically like that, okay? Now, those are points, right? Now, before I move on, if I were to basically try and draw a vector, A, I could call that 2, 3, -1. And basically, it would be the same thing, but rather than drawing a point there, I would draw a vector, okay? And vector B, which I'll make in orange as well, which would be -4, 0, 2. I would essentially do like that, and there you have it, okay? So the difference between a point is just, well, a point is hanging out there, whereas a vector is it's an amount of motion or movement or velocity or force or something that's in a particular direction, right? And so these Cartesian vectors, the ones that we're studying now, as opposed to chapter 6, the previous ones, they allow us to put a three-dimensionality on these vectors that was difficult or cumbersome in the previous unit, all right? So basically, a position vector is essentially what we were talking about there. So R would be a vector R1, R2, and R3. The reason why they use R here is because you kind of imagine a sphere. Oops. Right? A sphere. And so let's say I've got some kind of vector R1, R2, and R3. So I'd go like that, and like that. That would be the R vector. okay, and where this is R3. And what you're looking at there is essentially, you can kind of think of this as a radius of a sphere, right? So there's like a big sphere hanging out here, and you know, your R vector is sort of the radius to a sphere. But that's why they give it the letter R. But really, what it is just it's pointing to a position in space rather than having a point, right? In space, you actually can have a vector that points to a point in space. And why is that convenient? If you'd rather have it so that it can interact with other vectors, then position vectors are better than points, because you can add a position vector with another position vector to get a new position, for example. Whereas, adding 2 points together is something that we don't really necessarily do. Okay. Because, like, what's the sum of point A and point B? I mean, you could say that it's A1 plus A2, but at that point, you're basically just saying you're adding two vectors. Okay. Now, in unit vector notation, this is we're familiar with were the I, J, K vectors as well. So I could say a vector is, for example, maybe 3, 4, 5. This is the square bracket way that our textbook uses a lot. But I could also write 3i plus 4j plus 4k. And so the only new thing here is that the k vector represents the z position. The z dimension. Okay. We already talked about the I and the j vectors. And so you would just basically tack on at third, what's that called? Dimension. Okay. That's another nice thing about three-dimensional Cartesian vectors is they're basically behave exactly the same as a two-dimensional Cartesian vector. All right. But you just tack on another vector dimension. So speaking of that, how easy is it to find the the magnitude of a vector? Let's say I've got 1, -2, 4 as a vector, right? So we would know that that's a vector 1 in the x direction, 2 to the left, or right, I guess, and then 4 up, right? And then what would it be its units? Well, who knows? It's, whatever units you happen to be dealing in, that's its vector. It could be a position vector, it could be a velocity vector, it could be a force vector, right? Could be a lot of different things. Question is, what's the magnitude of this vector? Well, it's not apparent just looking at it, right? It turns out you can actually determine the magnitude of this vector by doing 1 squared plus -2 squared, and bang, you actually just put the 4, tack it right onto the end there. This is the three-dimensional Pythagorean theorem, if you will. And so you end up with a root of, 21 as the magnitude. Okay, pretty cool. And so it's essentially just you take your x and your y direction, and then you just add on to the z direction. It's the same as the magnitude vector in 2 dimensions. Magnitude of a vector formula for 2 dimensions. All right. Multiplying a vector with a scalar. Let's say I've got a vector b. That's 3, 2, 1. And I'd like to figure out what is 2b. Well, it's just 2, 3, 2, 1, written like that. And guess what? It's just going to be 6, 4, and 2. It's that easy, right? Adding and subtracting vectors. So let's say I've got a vector A that's 1, 4, 6, and a vector B that's -1, 0, -3. What is A plus B? Well, in 2 dimensions, you just add the first components. So it's going to be a new vector. That's going to be 1 plus a negative 1, right? So I'm basically taking those guys. And then I'm doing 4 plus 0, and then 6 plus a negative 3. And that is what A plus B is. Okay, and so it's just going to be 0, comma, 4, comma, 3. And if you were to draw this out, these are tough to draw out 3-dimensionally, but if you were to draw this out 3-dimensionally, you would see that basically what happened here is you could draw out the vector A, and then at the end of it, you would write, go negative 1, 0, and 3 using basically the vector B. And essentially what you would have done is if you start at A and you finish where B is, you basically achieved this vector, right? It's just a vector addition. You look at it if you were to draw a picture of it, it would just be that, right? In fact, we could try that. 1, 4, 6. It's going to be tough. Let me start so that I can zoom in a little later on. I'm going to do, so let's see, 1 in the x direction, 1, 2, 3, 4 in the y direction, and 1, 2, 3, 4, 5, 6 in the z direction. Okay. So it's like, and now basically I'm going up 6 to right around here. This is vector A. And now basically at A, I'm going to go negative 1 down, because now I'm going to do B, which is that right there. Whoops, crossed it out. I meant to highlight it. Now I'm going to do B, which would be 1 down, 0 in the, 1 in the x direction, 0 in the y direction, and negative 3 in the z direction. So 1 in the x direction for B would be sort of just another 1 out like this. Okay, that's 1 out. 0 in the y direction and 3 down. So 1, 2, 3, which would be like maybe half of this thing. And now that would be vector B. Okay. And then A plus B would be this thing, which if you look closely at it, it's 0 in the, oh shoot, I went 1 in the wrong direction. I meant to go like this. Shoot, sorry guys. 1 back and 3 down. So B should have been right there. Uh-oh. I'm going to have to erase some of this stuff. Like that. And like that. 3 down. So now the new vector, A plus B, is this right here. And if you look closely at it, it's 4, 0, 0, 4, and 3. Or whatever that happened to have been. Yes. 0, 4, and 3. Going back to that. So 0, 4, 3. Because notice I've gone 0 in the x direction. This is A plus B. 4 in the y direction. And 3 in the z direction. This is B. Anyway, I was just trying to show you. It turns out to be not easy. A unit vector. All right. So there's two things. There's the unit vector notation where you use I, K, and J. Okay. This is big, so make sure you pay attention to this if you're, writing. If you're watching this video, this is sort of a big concept that a lot of students get confused because this word unit shows up twice. All right. There's the unit vector notation where you use the I, J, and K in order to delineate or name vectors. Some textbooks use this. My physics textbook, for example, uses almost exclusively the I, J, K vectors. Then there's something called a unit vector itself, and it's got a U, right? And basically what it is if I've got a vector A that's maybe 3, 2, 1, for example. Now I can make a vector. Now what's the magnitude of this vector? Well, let me just say the magnitude of this vector is 9 plus 4 plus 1 rooted. So 9, 10, 11, 12, 13, 14, root of 14. Okay. And there we have it. That's the magnitude of that vector. Okay. Now, let's say the problem with this vector is it's not, it's square root of 14. Well, I don't know what the square root of 14 is. Let me see, actually. 14 square rooted, square root of 14. It's around 3.75. Around 3.75. So that's not 1 unit long. It's almost 4 units long. Okay. Now, if I want to basically use the vector A, and I want to preserve only its direction, but I want to kind of cancel out its magnitude, then basically what I want to do is I want to make what's called a unit vector for A. All right. And sometimes you can put a little a down here, the unit vector of A. And basically what I do is I take A, well, I'm going to make this bigger. I take A and I divide each of its components by its own magnitude, which I'm going to use root of 14. And root of 14. All right. And basically what I've got here is I've got a vector now. I have a vector that's exactly 1 unit long, but it's parallel to A. So this unit vector is parallel to A, but the magnitude of A is 3.75, but the magnitude of this unit vector is actually 1, right? So this is what's called the unit vector of A, all right? And why? Let me repeat why we're doing this. Basically, what we're allowed to do, you can do this by creating a vector. It allows you to create a vector that's parallel to another vector, or maintains its direction, but it has a unit of 1. Why would you want to do this? Well, in case I maybe want to multiply it later or into something, but I don't care about its magnitude. I don't want it. I want to conserve the magnitude of the other vector. So when you multiply things by a magnitude of 1, then like 1 times anything is just itself. And so what happens is you can kind of now, in a way, preserve the direction here, right? Or let's say I just want to make a magnitude. I want to make a vector, but for another reason. Let's say I want to make a vector that's parallel to A, but it's exactly 10 long. Well, first, 10 units long. First, what I would do is I would make the unit vector for A, and then I would multiply it by 10. And therefore, what I've got is I've got now a vector that's parallel to A, but I can create it any magnitude that I want. Okay, just to verify that this is 1 unit long, let's figure out the magnitude of u. The magnitude of u is 1, but let's figure it out. So it would be 3 squared over the square root of 14 squared plus 2 squared over the square root of 14 squared plus 1 squared over the square root of 14 squared, which is essentially 9 plus 2 plus 1 over 14 over 14 over 14, which appears, in my view, to be the square root of 14 over 14, which is 1. So notice what we did there is we just took this vector A, we figured out its magnitude, 14, root of 14. And we took that vector A and divided it by its own magnitude. Every component, basically. And as a result, what we've done is we've basically taken something that's 3.75 long and we've divided it by 3.75 and we've made it length of 1. All right. So now I can take this vector u and I can multiply it by 100. And now what I've done is I've got a vector that's parallel to A that's exactly 100 units long. If, for example, that's what I needed to do in my question, or for whatever reason. All right. Moving on. Find the vector between 2 points A and B. So let's say I've got a point A, which is 1, 4, 2. Let's say I've got a point B that's 1, 0, negative 3. If I want to find the vector AB, it's actually pretty easy. I just go 1 minus 2, comma, 0 minus 4, comma, and negative 3 minus 2. And I got negative 1, negative 4, and negative 5. And what this is vector AB. It's basically a vector that starts at A and ends at B and allows you to know essentially the magnitude. You can then figure out the magnitude. You can figure out the distance between points A and B by squaring these values, adding them and rooting them, different things like that. Finding the vector between 2 points is going to be extremely important next unit when we're talking about intersections of lines and planes and distance between points and different geometric shapes in 3D, which is basically the focus of chapter 8. We focus on lines, planes, and points and how they intersect, how far they are from each other, and different various things. Okay. So the distance between 2 points is basically, you first build the AB vector, which would be negative 1, negative 4, negative 5. I'll just use the same. And now to figure out the distance between them, basically you just figure out the magnitude of AB. And so that would be negative 1 squared plus negative 4 squared plus negative 5 squared rooted. And so we're looking at 17 plus 25, which would be 35, 42, right? Square root of 42. That would be the distance between points A and B. So you first find the vector AB, and then you find its magnitude. Okay, find the dot product. This one, it turns out to be very easy as well. This was that new operation. So again, let's give ourselves 2 vectors. Let's A, which is 1, 1, 1. Let's go 1, 1, 1 on this one. And B is 2, negative 1, 4. What's A dot B? Well, it turns out it's 1 times 2 plus 1 times negative 1 plus 1 times 4 for a total of 2 minus 1 plus 4, or a total of 5. And notice the dot product, the result of this is a scalar. It's not a vector, remember, okay, which is an important thing, okay? And, well, what's the applications of the dot product? Remember, we already talked about it. You can determine the angle between two vectors, even in 3D, using the dot product, okay, which we'll do down here, it looks like. Now, in 3D, we got parallel, and in 2D, we've got something called parallel. In 3D, you've got something called collinear, and it means the same thing, all right? So one way to discover if two vectors are parallel or collinear, it's basically means if their dot product is equal to the product of their magnitudes, okay? So basically, if I've got a vector, I'll write this out. A, which is A1, A2, A3. And I've got a vector B, which is B1, B2, and B3, right? A dot B, well, let me just write out A dot B. A dot B is A1B1 plus A2B2 plus A3B3 if that happens to be equal to the square root of A1 squared plus A2 squared plus A3 squared times the square root of B1 squared plus B2 squared plus B3 squared. Then, if these two are equal, then A and B vectors are parallel. A is parallel to B. Another actually easier way of doing this, though, another easier way of doing this is if A1 over B1 equals A2 over B2, and it also equals A3 over B3, then that's another way of determining if two things are parallel. So you've got this, or you've got this. I personally always use this lower one because it's really easy, right? So just an example. For example, we've got these two vectors here, A and B. A and B is 1, right? So I can now immediately quickly tell that these two vectors are not parallel because 1 over 2 divided by, 1 over 2 is 1 over 2, but 1 over negative 1 is not equal to 1 over 2. And so therefore these two vectors are not paralleled because basically in order for two vectors to be parallel, they're the ratios of their x components, their y components, and their z components must be equal, right? So that's an easier way of determining if two things are parallel, also known as collinear, right? All right, here we've got this. How do we discover if two vectors are perpendicular? Oh, there's a fancy word for perpendicular in 3D as well, and that fancy word is orthogonal. And you can figure out if things are perpendicular by seeing if their dot product is 0, right? So basically, if A dot B is 0, then A is perpendicular to B, okay? So we'll take this above vector. 1, 2. Well, we've already determined the dot product of 5. So in this upper, right, the dot product of A and B was 5, and so therefore we've concluded that A is not perpendicular to B, okay? Here's a bonus question. Sometimes you're asked to determine or build a vector that's perpendicular to B. Build a vector perpendicular to, let's say, A, which is 1, 1, 1. So I need some vector that's perpendicular to A. Well, what kind of vector? I don't know, any vector. And so essentially what I would do is I would say, well, A dot B must be 0. Okay. Well, let me do 1 times something plus 1 times something plus 1 times something else and make sure it's 0. Well, I got 3 things that are unknown here. Well, as it turns out, what you can do is you actually can just sort of make up numbers here. So I'm going to make up a number like 2, and I'm going to make up a number 2, and then here I won't make up a number. I'm going to leave this a variable, okay? And then as a result, what I've done is I've basically sort of, established my x and my y directions, but I've left my z direction variable, and now I just do a little bit of math, and I see that I've got a 2 here, a 2 here, right? A 2 here and a 2 here. So for a total of 4. So it looks like I have to have a -4 right there in order for this whole thing to be 0, right? So I would actually just do some math, and I would discover that z is -4. Do a little bit of algebra there. And so as it turns out, 2, 2, -4 is b, right? And this vector is perpendicular to A because its dot product is 0 when dotted with A. And I just made that vector up. I invented it. Okay? Now we can find the angle between two vectors, right? Find the angle between two vectors here. In fact, let's use these two vectors that we just used, and we're going to discover that the angle between these two vectors is 90 degrees, 1, 1, 1, because we just made it up, 2, 2, -4. Okay, so basically what I'm going to do here is I'm going to use this formula to determine the angle between two vectors. So it's the cosine inverse of A dot B, which is 1 times 2 plus 1 times 2 plus 1 times -4 over the magnitude of A, which is 1 squared plus 1 squared plus 1 squared, times the magnitude of B, which is 2 squared plus 4 squared. Oh, sorry, I skipped 2. 2 squared plus -4 squared. And then I stick that into the cosine inverse, and I end up with cosine inverse of 0 over, it appears that I've got the 3 root of 3 here. It doesn't even matter actually, but I'll figure this out anyway. This is going to be 1624 times 3, 70, 72. The root of 72. And now if I figure that in my calculator, boom, 90 degrees pops out. Cosine inverse of 0 over root 72 is 90 degrees. I found the angle between these two vectors, and I knew it was going to be 90 degrees because remember, way back here, I actually purposely built a vector that was perpendicular to vector A. Okay. So there's a couple of things. If you're familiar with the two-dimensional formulas, then the three-dimensional formulas are just, spin-offs of that two-dimensional formula where you just add in an extra dimension, okay? Tomorrow, or the next video, we'll talk about the cross product, okay? And the cross product is similar to the dot product in that it inputs two vectors, but it's different because the output is a vector, not a scalar, and it actually requires three-dimensional thinking because in order the two input vectors, the output vector is guaranteed to be uh, in a third dimension than the two input vectors, right? And so this concept will be exploited to answer a few application questions, just like always. All right. So there we have it. Couple of things to think about.